In a certain country, the shorthand of a clock is exactly half as long as the longhand, and rotates twice for each rotation of the longhand. In the diagram over here, the 3 points shown on the clock have accelerations of magnitude, the acceleration of point A, the acceleration of point B, and the acceleration of point C. And point B is at the midpoint of the longhand. So just note, since point B is at the midpoint of the longhand, and the longhand is twice the length of the shorthand, point B is at the same radius away from the center as point C. So, and when this is asking for acceleration, this is asking for the centripetal acceleration, or the acceleration required to keep this point moving in a circle. So the centripetal acceleration is given by the radius times the angular velocity omega squared. And it can also be expressed as the linear velocity squared over the radius, but we won't really be using this because it's just not very convenient to use this right now, since we don't know the linear acceleration of any of these points. Or, sorry, we don't know the linear velocity of any of these points, but we do know the angular velocity. So let's write everything in terms of the radius of point C and the angular velocity of point C. So with that, the centripetal acceleration of point C is simply going to be the radius of point C times the angular velocity of point C squared. So that's the magnitude of the acceleration of point C. And now let's figure out the other 2 points. So from this problem, we know that the radius of point C must equal the radius of point B. And the radius of point A is 2 times the radius of point C. So we can express this like that. So the radius of C and B is 1/2 the radius of A. And the angular acceleration of C, and it says that angular velocity, not angular acceleration. This is angular velocity. So the angular velocity of C is going to be twice the angular velocity of every point on the longhand. So it's going to be twice the angular velocity of B and twice the angular velocity of A. And this is because only the linear velocity is different at each point on the same radius undergoing circular motion. And the whole line undergoing circular motion has the same angular velocity at every point. So with that, we can write an equation for the centripetal acceleration of A. Let's start with A. So we know that the radius, we need 2 times the radius of C to equal the radius of A. You can simply say that the radius of A is equal to 2 times the radius of C. And we're converting this because we're expressing everything in terms of the radius of C and the angular velocity of C. And the angular velocity of A is 1/2 the angular velocity of C. And we're going to square that. So this becomes equal to 1/2 times the radius of C times the angular velocity at point C squared. So this is also equal to 1/2 of the magnitude of acceleration at point C. Now let's go to the acceleration at point B. So we know its radius is the same as point C. We know that. And the angular velocity, again, is the same as point A, which is 1/2 the angular velocity of point C. And this is going to be squared. So we end up with 1/4 times the angular acceleration of point C, or not centripetal acceleration of point C. And this is simply 1/4 the centripetal acceleration of point C. So if I clear this up a little bit, just get rid of all that. This is what we get. So this is simply just the centripetal acceleration of point C. So from this, we can see that the acceleration of point C is greater than the acceleration at point A, and that is greater than the acceleration of point B. And that is how these three centripetal accelerations would compare.